Hello there. I'm Tim Baarslag. I'm a professor in mathematics of Cooperative AI in Eindhoven and a senior researcher at CWI, the National Institute for Math and Computer Science in Amsterdam, where I lead the Intelligent and Autonomous Systems Group. And in short, I'm interested in how we make joint decisions, even when we want different things. That is, I work on the mathematical foundations of cooperative AI, designing mathematical models and developing algorithms so that computers can make joint decisions with each other and on behalf of us. Think, for instance, of the smart grid, in which computers have to negotiate complex energy contracts for us multiple times a day. Or think of autonomous vehicles that need to decide jointly on who gets priority on an intersection, striking a balance between speed and fairness. Or the trading of goods and services. This could be, for instance, supply chain management or real estate negotiation or even kidney exchange. And this process of joint decision making is called negotiation. And this is how we normally represent a negotiation, with our utility and the opponent utility on the axis. And every dot is an outcome that specifies values for multiple objectives, for instance, a smart grid contract here. And the desired or Pareto optimal outcomes are in the top right. And these are the ones that we want to get to, so B dominates outcome A here in some sense. And it can be viewed as a game with private information in which I start with a very good bid for myself, then the opponent is their turn, and then we make a concession and we slowly explore this space together until we reach an agreement. And this is not easy because I have a private set of acceptable outcomes, and so does my opponent. And only in the intersection of these is the zone of agreement. And this one of these will be the eventual outcome. So which one will it be? Well, that is determined by who is the best negotiator or who has the best negotiation algorithm. And this is hard because, in fact, the big challenge is that you don't know exactly how good outcomes are for the opponent. In fact, the diagram gets all fuzzy on the vertical axis. Luckily, we can learn a lot from the opponent's bid. For instance, if your future boss keeps offering low salary, then probably finances are very important to them. So we can use methods from machine learning, time series regression, and convex optimization to look for patterns and trade-offs in the opponent's bid. Another challenge is bidding, so what kind of concessions we do on the horizontal axis. Think, for instance, about buying a house where mistakes can be enormously costly. So for that, we need to maximize expected utility under uncertainty and possibly a huge space of potential outcomes. We can use techniques from simultaneous search theory, for instance, to find optimal concessions effectively. And the last one is about accepting. Bids come in, and because the opponent does not know our preferences either, they behave stochastically in our utility. This can be seen as a sequential decision-making problem of when to say stop and say, yes, I want this bid. And we can use optimal stopping theory to establish the best time to accept. And finally, an additional challenge is to teach computers of how to represent us in these types of negotiations. So to do that effectively, the AI needs to obtain some sort of accurate user model through preference elicitation, so by asking questions, usually to get a sense of the user's trade-offs without causing too much bother. And therefore, cooperative AI has to perform these tasks with limited preference information. So the outcome space becomes all fuzzy, and this is still largely unexplored territory. What is the value in acquiring more information? So just to give you some mathematical intuition, finding the right query comes down to finding the optimal query queue, such that on average, for every possible response R that the user might give you, we need to maximize our expected utility when we make the optimal decision pi after updating our user model, from which we subtract the costs of posing the query queue. And we really require new decision theoretic solutions for these types of problems that are entirely intractable otherwise. So since this is quite a recent field of research, there are many exciting open problems which I try to tackle in my research. For instance, making partial deals with multiple opponents at the same time. How do you do that? Or negotiation with humans using natural language and LLMs, which we do in an international competition. And what if everyone is using AI to make decisions? Then we get to equilibrium strategies, which we can study with game theory. But in the end, what connects all these problems is the need to understand the mathematical underpinnings of joint decision making so that we can design AI that is truly cooperative. Thank you.